Alright, so we're going to be proving Fermat's theorem in this video. So what Fermat's theorem says is that if p is a prime number and k is not a multiple of p, then k to the p minus 1 power is congruent to 1 mod p. So to start this off, we're going to start with a quick lemma. So from the modular arithmetic practice problems, we know that if A is congruent to B, mod M, and C is congruent to D, mod M, then A times C is congruent to B times D, mod M. Okay, so we're going to use that later. Alright, so to start off, for this lemma, we're going to say let n be greater than or equal to 1, because we need our n to be greater than or equal to 1, and any prime number is greater than 1 anyway. So we know that a remainder n is equal to r minus q times n by the definition of a remainder. So from here we can say that n divides qn by the definition of divisibility. We can also then say this implies that n divides a minus qn, because a minus a will just be equal to 0, and since n divides qn, n also divides negative q times n. From there, since addition is commutative, we can rearrange this to say that n divides a minus qn, which we can then rewrite to say that a remainder p is congruent to a mod n. Sorry, I'll put this as an n. Alright, so we're going to use that later. So now, the continuation of this lemma, so by this remainder 1 here, we know that if a rem p, we'll use p now, is congruent to a mod p, and b rem p is congruent to b mod p, then we can say by this number 1 here that a rem p times b rem p is congruent to a times b mod p. And this will work regardless of how many factors we have, because we can just call this a times b term our a, and then if we have a c, we'll just call that our b, and it works for any number of factors. Alright, so from there, we're going to go to the lemma that I proved in my earlier video, which said that m times k rem p takes on all values from the set 0, 1, 2 up to p minus 1. That was proved in my previous video. From there, we're going to refine that a little bit. So we're going to say let m equal 0. So when m equals 0, we can say that 0 equals 0 times k rem p, because this here will just be 0 rem p, which is just 0. Alright, so we know that from the earlier lemma that this has to take on a unique value for every value in this set as m goes from 0 to p minus 1. And we know that the only time this can be equal to 0 is when m equals 0. So what this means is we can say that m times k rem p takes all values in the set 1 to p minus 1. Basically, we can just eliminate 0 from both sets and still have the same result. Alright, so from here, we're going to go, so we're going to use this, we're going to go back to our original Fermat's theorem. Alright, and so from there we can say that 1 times 2 times 3 times ... up to p minus 1 is congruent to 1 times k rem p times 2 times k rem p all the way up to p minus 1 times k rem p, mod p. And we can say that because since m times k rem p is going to take on every value in this set 1, 2, 3 to p minus 1, these values are all going to be the same. They'll just be in a different order, but that doesn't matter for multiplication. So from there, we can say this implies that p minus 1 factorial is congruent to k times 2k times 3k times p minus 1 times k mod p. And this is by the lemma 2 that we just proved. Okay, so from there, we can rewrite this to say that p minus 1 factorial is congruent to p minus 1 factorial times k to the p minus 1 mod p. Okay, so from here, because p is a prime number and we know k does not divide p cannot divide p minus 1 factorial. So from the cancellation proof that Brian did in his first video, we can cancel out p minus 1 factorial from both sides, and that leaves us with Fermat's theorem that says 1 is congruent to k to the p minus 1 mod p.